but chances are you're going to get the hell out of here after class, I'm imagining. But when you have bell-shaped data, and that's Patty, this is the big point. The reason I did the cart before the horse thing was because we had to get the bell up there first, because this only works when you have bell-shaped data. And that's a big caveat. That's a big caveat. If your data is, now, your choice. We can call it bell-shaped, or let's just call it bell-shaped. You guys are used to that phrase, I think. I was going to call it symmetric unimodal. Okay, then I won't. Just call it bell-shaped. If your data is bell-shaped, the first thing is feel pretty good about the average. Feel pretty good about using that average. X bar. And why do you think I say feel pretty good about using the average X bar? Nice! There's no skew. Remember the issue with using an average when you've got like highly skewed data or bimodal data? The average might be in a place where your typical data isn't. So going back to the idea of typical versus atypical Carly brought up, when you've got bimodal data, your X bar might be right in the middle of the modes. So you go, oh, my class is doing fine on average. Yes. Yeah, but on average, they're not doing anything. They're not getting a 70. They're getting an F or a D. It just so happens that the three people that got 150s pulled the average away from that typical. So the idea of feeling good about using the average X bar is that a lot of your data is close, quote unquote, to that average. The average is not getting, the average is a pain in the butt, and here's why. It's a beautiful measure, but it's also ADD. And here's what I said by ADD. It looks at the entire data set and it watches like this. And then as soon as an outlier shows up, it goes, ooh, 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 and it wants to go play with the outlier. The median's like, dude, it's an outlier, let it go. It's just, watch, it's not gonna happen again. Oh, it happened twice? Dude, there's like 200 data points over here. Focus, focus! But the average is like, ooh, ooh, it wants to go play with the outliers. It heads towards the outliers. So if you have bell-shaped data, it gets pulled equally on the left and the right because the bell has outliers here and here. There isn't just one tail pulling the average. Does that kind of make sense? So that pull cancels and you're central. Beautiful. That's one thing. So feel good about the average, number one. Number two, you get these cool percentages. You get these cool percentages. Here are a few of them. I'm going to put certain percentages exist within standard deviations. I'm going to put those in quotes. Standard deviations. So here are the most popular. Here are the most popular. I'm going to give you 4 of them. You've already established 2 of them up here at the board. You've already established 2 of them. A, about 2/3, or I think the number that's used very often is 68%. I mean, they're close. I think this is probably closer to the literal truth of what is actually in a perfect bell curve. But I think 2/3 is easier to remember. Or 68% of the data is within 1 standard deviation of the average. Let's make sure we understand this sentence before I go any further. This is just algebra speak for 1 standard deviation from average. Take the average, add and subtract S from it. That sets up a range of values. If the data is bell-shaped, unimodal bell-shaped, you're going to get about 2/3 of your data in there. Go, Carly, go.
For all bell-shaped data?
Yes.
Okay.
That's the best part. Now, what Carly's thinking of is, wait a minute, time out. What if the bell gets squashed? Is that what you're thinking? Something like that, or it's super tall? So Carly's thinking about, can I come back to that? We'll finish with that. I love that question. Thank you. I love it. And it actually is very applicable in this class. More later, but it's a fantastic, yeah, let's come back to that. Great question. Another one that's very popular, and this is probably the most popular one, STAR. And I'll put it there for those of you not taking 244. We got 94% within 2. The guideline is 95. And if you actually look at the curve, it's closer to 95 than 94. About 95% of the data are within 2 standard deviations. Sweet. Those are the two that we just experienced. There are two other ones that are not as popular, but I think just as important. Almost all the data is going to be within 3. Almost all of the data is going to be within 3. Now I say almost. It's not 100%. It's not 100%. But the lion's share, I think it's 99.75% or something like that. Like, you got to be really, really outlierish to be outside of 3. And we'll come back to that. There's a meaningfulness to that that actually exists with your cell phones that's outside of 3 standard deviations. We'll talk about that more on Tuesday after this. Let this wash over you a little bit. And here's one of my favorites that hardly ever gets talked about. Like, these are all great percentages and all, especially 100. How far out do you think you have to go to get half the data? The middle half, the middle 50%. In other words, average cuts it in half, correct? Average cuts your data in half left to right. But how far out would you have to go to catch the middle 50% of your data? What do you think? Gut.
Half a standard deviation.
A little bit more. Very nice. I think it's 2/3, closer to 2/3 of a standard deviation. If you go out 1, you've gone too far, correct? If you go out 1, you've got 68 2/3. But if you go out about 2/3 of a standard deviation, you actually catch about half the data. Yeah, about half the data are going to be within 2/3 of a standard deviation. Isn't that wild? Now you can see, just like, rule, damn it. If you have to go out 2/3 of a standard deviation to get half the data, why is it 3 to get all of it? Wouldn't it be just twice as far? 2/3 would be 4/3. Doesn't that make sense? 2/3 get you half, 2/3 more get you the other half. And this is where the mathematics kicks in. What's the curve doing as you get further from average? It's dropping rapidly. So in order to pick up more data, you have to go further out to pick up more data. The lion's share is clustered right around that middle. So that middle 50% is very, very tight. The outside 50% is extraordinarily scattered by comparison. You see what's going on there? That's the mathematical logic of it. Now, Carly, I want to finish with your comment. We'll come back to this on Tuesday. You've got enough now under your belt to do what's on the exam, and you also have enough to do what's on the quiz for next week, but we're not done with this yet. Carly asked a question about, does this work for all bell curves? Yes. And bell curves can change. They can be taller and skinnier. They can be shorter and fatter. Let's come over here. So here's a bell curve. Ish. Here's one too. Right? And then here's another one. Here's another one. The taller a bell curve is, the tighter around average it is. Which means the standard deviations are smaller. Small s value. Same 68% is trapped, but it's trapped in a narrower region. The wider the bell curve is, it's got to be shorter to catch it. Now there's a reason why they have to change it independently. You can't just draw any old bell curve and be like, oh, that's a good one. There's a function governing it. And that function, by definition of that function, you have to capture the same percentage with it. More on that to follow, but that's a quick answer to your question. Is that good?
Yeah.
Awesome question, thank you.
Sean, can I ask you a question?
Of course!
Okay, so in the beginning we went out 16.
We did.
That was one. And then we went out 16 again. That was 2. And we went out 16 again.
That would be 3.
So we went out again. Would we go 8?
You go 16 more.
Okay. So that's
Yeah, the 2/3 would be 2/3 of S, 2/3 of 16. Which would be, what would that be? 11, 12, 11 and a half, something like that. 2/3 of a standard deviation would be going on 11 and a half. Exactly. No, 16 would be a whole number of standard deviations. Think of this as multiplication. This number times whatever S is. So 1 times S is 16, 2 times S is 32, 3 times S is 48, 2/3 times S is 11 and a half. Yeah, it'll make more sense, I promise. This is what we're not done with this yet. Nowhere near done. Thanks guys, have a good weekend!